Good morning, everybody. Thank you for joining us today for our webinar, Optimizing Strain Gauge Location Using TrueLoad. Just to give you guys a quick overview, this webinar will be about 45 to 50 minutes long, and we will have a Q&A session at the end as well. So if you guys come across any questions throughout the presentation, please feel free to ask us at the end. There's a little Q&A tab that you will see at the bottom of your screen, so you can type any questions over there, or you can send it us via chat as well. So I would like to get started with an introduction to Shrikant. He is going to be doing a bias introduction in just a little bit. And so Shrikant is the Director of Software Technical Services at Bias with over 10 years of Abacus experience in customer support and consultancy for a range of diverse industries. He graduated from Brown University with a doctorate in solid mechanics and master's in applied mathematics. He has experience in various structural and thermal procedures of Abacus and its features with specific focus on connectors, Abacus diamola co-simulation between different Abacus products, discrete elements methods, contact, and constraints. His email is listed on our screen, so if you guys have any questions, you can email him directly as well. I would also like to introduce Tim Hunter, who will be presenting the TrueLoad webinar today. And Tim is the founder of Wolfstar Technologies, an engineering consulting and software development firm, which concentrates on the efficient use of FEA and test data on engineering problems. Tim brings 30 years of product development experience to his clients' projects and innovative software. Tim earned a bachelor's degree in mechanical engineering from Marquette University and a master's and PhD in engineering mechanics from University of Milwaukee. So thanks, Tim, and thanks, Shri, for joining us today. And Shri, we can get started with a biased intro.
Thank you, Kanis. Hello, everyone. I'll briefly present our company's the processes, what we do, and what the activities we indulge in with that. And let me get started. I'm trying to go to the next slide here. Okay, so be a brief company overview. Who we are a platinum partner of Dassault Systems, Simulia. Some of you may be familiar with that. Products they have is Abacus, iSight, FESafe, and Tosca. But also there are other brands of Dassault Systems like KTR, Delmia, Innovia 3D Experience. We are having a team from with multiple industry experience. Oil and gas is one of the primary ones, but there are other industries like machinery, equipment, petrochemical and processor industries, nuclear, aerospace, medical devices, manufacturing, and automotive. So any particular problem that you may be facing, we could help you with that in belonging to any particular industry that you may belong to. We are present in Houston as our headquarters, but also we have offices elsewhere in the United States, in Chicago, Cincinnati, San Francisco. Our team consists of various like PhD and master's degrees within different departments of or fields of engineering, like solid mechanics, fluid mechanics, materials and corrosion, numerical analysis, optimization, reliability, and data analytics. We have expertise covering a wide range. Our primary activities include consultancy, engineering consultancy, and PLM also, product lifecycle management. Also, we provide training for the software that we sell, Dassault Systems products specifically, and also software sales we can do, again, dealing with Dassault Systems products. We also help you with the support and anything like any questions that you may have in using the software, that we can help you out, and also in developing any kind of a customization automation scripts that you may need to improve your workflows. So feel free to reach out to us if you have any questions or particular needs. Definitely we could look into that. A little more detail about our technical capabilities. We can take up specific component design and validation using simulation, say products like Abacus or ANSYS, anything that you may like to have. And then FEA-based fracture. We also develop what you call as, we will also look into the in-service components, where how long they can last and what the durability and so on, that we can look at. We also can optimize your designs for improved performance and say increased strength with a reduced mass and so on. We can also do some structural analysis and vibration assessment for your existing machinery or for any future design that you may be working on. We can also do actually electromagnetic systems simulations, again using some CST, which is a product of Dassault Systems. And then again, we can deal with mechanics too. So basically the CFD part. So that way we can offer some kind of a multi-physics simulation where you can have a fluid and structural interaction included in it, or it could be purely a fluid domain problem also. Then we can also work with you for any fatigue analysis that you may want to have. Again, it could be a strain-based or stress-based analysis. And again, we have good expertise in composites too. So that way, that we can actually, you can leverage our expertise for any composites that you may have in your products. And then automation of simulation itself, something that improves your performance, that we can look at. And also we also can work with a digital mock-up development and systems engineering too, like electrical cabling, piping and ducting and so on. So as I mentioned here, we have a wide range of expertise covering various aspects of simulation and design processes. So please feel free to contact us if you have any particular needs that you would like to address. What kind of value proposition we bring to you? We actually are very much dedicated to client success. In their satisfaction we'll take immense pride in that. We also try to bring innovations and technical excellence in any particular project that we deal with. We have a strong expertise in FEA and CFD, and again, as I said, spanning multiple industries. We can also review your existing simulation workflow process and provide you with some feedback that may be of some help to increase your performance and also usability. We actually offer trainings, dedicated trainings, or even customized ones that are specific to your needs, also standard ones that are available from, say, Dassault Systems standard lectures. We can provide that at your site, or even on our site, or even online. So whatever works out for you, we could customize the trainings accordingly. And lastly, we also have software development services for Abacus, which include developing user subroutines, maybe specific user elements, which the elements that are not available in a standard Abacus code. Also Python scripts that can help in pre and post processing features or processes, and also calculations. With that, there's a contact info given below, so feel free to contact us for any of the consultancy, software sales, training, and support that you may have. We'll definitely try to do our best to help you out. With that, I will pass to Tim Hunter for the presentation, and I'll stop sharing the screen.
Okay, thank you, Shri. I'm just going to get set up here real quick. All right. Okay, so thank you all for joining us today to learn about optimal strain gauge placement with TrueLoad. We're going to go through a lot of background here. I've got the overall background, I've got detailed theory, and we've got a number of customer examples. This is about 40 to 45 minutes worth of information here. So I'm going to get through it, and we'll leave time at the end for questions. So thank you very much for taking the time to join us today. The little example you see on the screen here is a fun project we did with the University of Wisconsin-Milwaukee with your SAE Baja team, and we'll get into details with that at the end. But it kind of shows you the type of things that we can do for using the FEA model and strain gauges to back calculate load. So that was a very exciting project, and it worked out really well. So we'll get into all of these things later, and we'll just get right into it. So just a little bit of background about Wolfstar Technologies and myself. Wolfstar Technology was founded in 2010 by me, by Tim Hunter. I'm the president and founder of Wolfstar Technologies. Prior to founding Wolfstar, I was at Harley-Davidson for 22 years as chief engineer of vehicle structures. I've been through every aspect of product development. I've worked with styling and marketing. I had a staff of engineers, design engineers, test engineers, analytical engineers, worked with manufacturing, worked with late design changes, worked with supporting the plants and launching product, and even worked with customer issues in the field. So I fully understand what all of you go through every day in developing product. It's a tough thing to do. You've got to meet everybody's needs. You've got to deliver good products to people and do it in efficient fashions. And I think what you're going to see today is that we've got a tool here that can really help you out in supporting that whole workflow better. Since we launched our company, we've got great partners of Dassault Systems, ANSYS, MSC, and CE-Tron. CE-Tron is what we use for our 3D visualization. And these companies have seen the value in our product, and they want to help us get it to their customers so that their customers can use their tools better and more efficiently to develop product. So we're all about working with the FEA systems and helping you drive your designs and get them to be better designs. And this is kind of the takeaway. Really, TrueLoad gets, only with TrueLoad can you use FEA and test to understand all of your product loading. So we can understand extremely complex loading on products with using your FEA model to work with your test data and back calculate those loads. That's really what we're all about. And this is just a snapshot actually from our webpage. I just took the snapshot today. So this is a list of a lot of our clients. And you can see we've got a lot of Fortune 500 companies as our clients here. And the ones highlighted in green, these are companies who are actually either TrueLoad customers or they have used TrueLoad. We've used TrueLoad on their consulting projects. So these are companies who have seen the value of TrueLoad in helping them develop their products to understand their product loading in real world situations. So we've got a great suite of customers here that really use our products and can tell you all about it. So the products from Wolfstar Technologies, our flagship product is this product we call TrueLoad. TrueLoad basically turns components into load transducers, and the way we do that is we basically have you set up an FEA model, you apply a bunch of unit load cases to it, we tell you where to place strain gauges, and we extract a correlation matrix that relates strain response to all the unit loads in the model. And then you go place the strain gauges on the physical part, measure the physical strains in the physical part in its operating environment, and then we'll use those physical strain measurements to back calculate the loads. We're basically just making load transducers. We're turning your parts into load transducers, and we're leveraging the FEA model to do that, okay? We're making load transducers, that's about it. The second tool from Wolfstar Technologies is a product we call TrueQSE. QSE stands for quasi-static events. And basically, this will take individual result sets from your FEA model and allow you to linearly superimpose them via user-defined functions. And that capability by itself is really great, but what happens is that when you use TrueLoad, TrueLoad's going to develop time history of loading that map back to individual result sets in your FEA model, and then TrueQSE becomes a tool that you can go in and post-process and plot XY plots anywhere in your model or do operating deflection shapes on the loads that you've just measured. So TrueQSE is so important for understanding the response of your model that we bundled TrueQSE into TrueLoad. So when you buy TrueLoad, you get a license of TrueQSE automatically. And then the third product from Wolfstar Technologies is a product we call TrueLDE. LDE stands for Linear Dynamic Events. And basically, this is an FEA-only post-processor for linear dynamic solutions. So basically, it can work with time domain, frequency domain, and PSD domain solutions. So most of the post-processors out there are really oriented around the static type analyses. And this is a post-processor that's specifically tuned to the needs of the analyst working in a time varying or frequency varying domain. So there's tools in there that makes doing the post-processing intuitive and easy and extremely quick. So LDE is really an analysis only tool. And then all of our tools are so focused around making sure that you're getting loading right. Once you've got the loads correct, we've got tools built into all of our products that basically automatically will set up your runs for your basic FEA-based fatigue products. So products like FE-Safe. So we can dump out the information to FE-Safe directly to set up your loading information for your fatigue analysis in FE-Safe. And so that makes using FE-Safe and other tools very intuitive and easy, and it can just make it basically be a button push. So if you've got FEA-based fatigue, we make using that software much easier, but you don't need it to use our tools because our tools are all about getting the loading and having you understand the operating deflection shapes of your structure. Okay, so the whole motivation for TrueLoad is quite simply, what's the load? So if you're a design engineer that's got to design parts for this motorcycle, and the loading on this motorcycle is crazy nonlinear. You can't measure the loads, you can't simulate the loads, but you as a design engineer, you as an analyst have got to develop product that functions and is durable. Well, what can you do? How can you do that if you can't understand the loading? Well, what we recognize is that the individual components are basically responding linearly. So we'll place strain gauges on the swing arm, on the frame, on the crankcase, on the handlebars, on the fenders, on the gas tank, on the luggage system. We'll turn the individual subsystems into load measuring devices, and we'll measure the real-time operating loads from these structures, and then use those loads to do design and development and to help you optimize those parts. So that's how you can do the design. Otherwise, you're just guessing. So this is all based on this is a first market technology, and it's all based on a technology called influence coefficients. Influence coefficients have been around for probably 50 years or so, but historically influence coefficients have always been best guesses for strain gauge placement, and then the correlation matrices were unstable, and it never worked very well, and it was all very manual and in the lab. And what we've done is we basically have leveraged the FEA model and scripting to give you optimal gauge placement so that you've got the most stable correlation matrices when you go to the field. So a little background here, historical concerns with loading. When you make an FEA model, you can have a great CAD model, you can have a great mesh, you can have a great material model, you can have a great solver. But oftentimes when you go to throw it in for that solve, you're oftentimes guessing at what the load case is. You might do a calculation on the back of a napkin, you might have some departmental rules for some of the loading, but at the end of the day, it's more or less a guess because you don't know what the actual load is on the structure. And then if you're guessing at the loads, you're basically guessing at the solution. And then you end up going through extra iteration cycles. And people try to mitigate this by using tools like you see here. These load transducers here on the screen, these are perfectly fine devices. But the problem is that these devices are expensive. And every time you use one, you've got to modify your structure. You've got to cut out material, insert the load transducer. Now you've just changed the mass, you've changed the stiffness, you're measuring something, it may or may not be the actual load. And then worst case now, you bring it to the analyst, and the analyst is typically working on the as-designed part. Now the analyst has got to take his FEA model and rework it to look like the test part in order to use the loads he just measured. So it's not a great solution, but this is traditionally what people have got to do. Another approach that people try to use are strain gauges. So typically what will happen is the analyst will look at their FEA model and look at the stress and strain contours on the FEA model, come up with some strain gauge locations. They might talk with their colleagues, come up with some more locations. At the end of the day, they might have 30 strain gauge locations. They instrument the component, they go to the field, they collect all this data, and they got this time series of data, and they look at the time series of data, and they look at the FEA model and just scratch their heads. They can't make any sense of what's going on. So what ends up happening is that you'll typically drop all but 1 or 2 channels of data at 1 or 2 points in time, and you'll come up with load cases that just matches qualitatively, not even quantitatively. And you'll say, that's my load case I'm going to use for redesign. And then the next time you get to the field, you end up having a situation where the problem repeats itself on your next prototype, or you've got a new problem that you didn't even think was going to happen. And so then you just go through the whole cycle all over again. I have done this in my past. I'm sure you have done this. This is just a problem with doing FEA. So what's wrong? Your companies are investing in the right tools, skilled analysts, world-class FEA software. They're doing the right stuff by testing, and even investing in tools for doing fatigue. So you're investing in all of the right tools, but not getting the right answers. What's going on here? Well, the problem is you just got too many variables. You've got the gauge locations, you've got the load cases, and you got the quantity of data. So if you had 30 strain gauges laid on a part, you go to the proving ground, you come back, now you got a time history of 500,000 data points. So this 500,000 data points, each point in time is going to have a unique loading recipe to create the strain at that point in time. So now you've got 500,000 loading recipes to do. So that's just something that you can't do manually. So you're just left with this no-win position, and you're just spinning your wheels. This is the problem. So the solution here is TrueLoad. TrueLoad is doing what's called in situ load measurement. So in situ means in location load measurement. So we're going to turn your components into multi-channel load cells. We can work with any FEA model you've got, any FEA system you've got, and your test data. And we've got really nice plugins for ANSYS Workbench, but Abacus Workbench and Abacus CAE. But at the end of the day, we'll get you optimal placement of strain gauges, and with those optimal placement of strain gauges, we'll give you strain correlated loading functions, and with those strain correlated loading functions, we can drive your FEA-based fatigue softwares. So this is what we're all about. This is the solution. So we have got applications in all of these product segments you see here. So if your structures are getting loading from the wind, sea, or air, if you're getting loading from your customer, if you're getting internal loading, we can help you back calculate those loads and understand the loading on your structures. Okay, so we can basically get at any problem you've got if your product is getting unusual loading. So this is the V diagram in product development. I'm sure you've all seen this. It's a pretty handy diagram, but really in product development, this is a pretty nice model. You start with the voice of the customer, you go in and get your product requirements and functional specs, and then you start getting into CAD and FEA, doing your system, subsystem, and component design. So this is all on the virtual side of things, trying to develop your product in an efficient fashion on the front end. And then when you want to start proving it out, you'll come back and you'll start with the component test, subsystem, system test, and all the way up to functional acceptance test, and then you can launch your product. So, and where TrueLoad fits in is TrueLoad is all about taking the data from your component, subsystem, and system tests and pulling it back into the virtual world so you can drive your designs and do the best thing by your virtual design. And we can go through this process fewer and fewer times. My customers end up eliminating entire iteration cycles. In fact, most of their iteration cycles once they get good at doing this, because they get their first prototype is going to give them the load that they need in order to do the right decisions later. So here's the workflow for TrueLoad. It's going to start off with your FEA model like normal. So this is just a normal FEA model, but rather than having come in with a complex set of loads on there, I'm going to have you decompose your loads into a series of unit load cases. So it might be 1 kilonewton in the X, 1 kilonewton in the Y, 1 kilonewton in the Z, maybe a pressure load, maybe a thermal load, maybe an inertial load. And the way you need to think about these unit load cases is if you could mix them together, could you approximate the operating environment of your structure? So this is you designing the load sensitivity to your part. So this is you setting up an FEA model, coming up with a bunch of unit load cases. You solve that then, you bring that into the TrueLoad pretest software, and the TrueLoad pretest software will look at the strain results for all those unit load cases and come up with the optimal strain gauge placement for the structure. And then we've got tools that let you reposition and reorient the gauges to make it easier for the test guys to lay the gauges. And at the end of the day then, we're going to extract a correlation matrix that relates the strain response of the gauges to each of the unit load cases. We'll store that correlation matrix off to disk, and then you'll take this information for the gauge placement, and you'll bring the gauge placement information into the lab, and you'll place the strain gauges on the physical product, and then you collect the strain data. So you could collect the strain data in the lab, you can collect it in the field, you can collect it in the customer's hands. So the whole idea is that we're measuring strain and time histories of strain data. And then we bring those time histories of strain data then into the post-test software, and the post-test software then is going to take the measured strain data and multiply it by the correlation matrix from pretest to generate us some loading functions. And now these are time histories of loads, and loads are loads are loads. So we can just bring those loads, bring them into our FEA model, and do whatever redesign we want to make whatever design improvements we want. And you could do that with normal manual means, but what I highly recommend is you use the TrueQSE software, which manages all of your unit loads and the corresponding loading functions very efficiently, and allows you to do very quickly tools for probing the model for any data component of response you want. We can generate operating deflection shapes, and then we can even work with your fatigue softwares and push data off your fatigue softwares, because now you've got strain correlated loading functions. Now those loading functions become your duty cycle, and that's the most important part of you doing fatigue analysis. So this looks like a kind of complex flowchart, okay? I get it. But really, the first 4 blocks are you turning your part into a load transducer. And then once you've got the measured loads, then you use those loads to do design and optimization. So you might do the first 4 blocks once, and then when you're doing your design and optimization, go through this process 20, 30 times as you optimize your part. So that's the basic overall workflow. So this is all based on a theory of linear systems and loads, okay? So a linear system is where loads are proportional to displacements, displacements are proportional to strains, strains are proportional to loads. It's a linear system. Now, I understand everything in life is nonlinear, okay? I get it. But what we're going to do is we're turning your components into load transducers. So we're going to target nominal areas on the structure where the strain response is remaining linear and nominal, okay? We are going to stay away from welds. We're going to stay away from areas of contact. We're going to stay away from bolted joints. We're going to be in nice nominal areas where we've got linear and proportional strain response. The loading can be as nonlinear as anything. The loading could be sinusoidal, it could be ramp loading, it could be impact loading. That's okay. We just need the strain response to remain linear and proportional. So I can take this diagram here, turn it into a couple of equations. So the right-hand side, well, that's F equals Kx. So if your structure is obeying Hooke's law in bulk, then the left-hand side of the triangle has got to apply. And this is what we use for TrueLoad. We've got a strain, we got strains times a correlation matrix is equal to load. And we're going to calculate loads as being strains from test times a correlation matrix from FEA. So this is what we're doing with TrueLoad. And I mentioned earlier that this is based on the science of influence coefficients. This is the governing equation for influence coefficients. So if you look at papers, you'll find this equation all over those papers. So another nice insight you can get from this slide is that this equation here, strain times C is equal to F, is basically the strain corollary for Hooke's law. So basically this tells us something about our FEA model. We need to be basically capturing the stiffness and mass of the structure properly on the structure. So we just need to have a good FEA model. We don't need to have every last detailed modeled on the FEA model. We just need to have something that's capturing the overall nominal stiffness and strain response properly. So the nice thing about this is our requirements for the FEA model are basically we need to have a good FEA model. We don't need to have the excellent FEA model. So this is an important thing. It makes doing it much easier. Okay, we're going to have several pages of math here, okay? So we're going to go through the details of the mathematics on this very quickly. So this is our equation for TrueLoad. So we've got strain times a correlation matrix is equal to load. And in this example, I've got 3 unit loads on my FEA model, and I've got 4 uniaxial strain gauges laid. So the columns of the strain matrix, each column represents a uniaxial strain gauge. So we're going to go through this row by row here and see what happens. So here I'm going to turn load case number 1 off, turn load cases 2 and turn load case number 1 on, turn load cases 2 and 3 off, and then we're going to measure the strain response at these 4 gauges. Okay, we'll write that down. So we're writing the strain response due to load case number 1. Now let's turn on load case number 2 and turn load cases 1 and 3 off. And now we go back, and at these same 4 strain gauges, we're basically recording the strain response. Now the strain response at these 4 gauges is going to be different because load case 2 is different than load case 1. So this is essentially a strain signature for load case number 2. So we write down the strain signature for load case number 2, and now we go on to load case number 3. So here we got load case number 3 turned on, load cases 1 and 2 turned off, and now we record load case number 3's strain signature. So now we've got 3 unique strain signatures, 3 unique load cases. This is a well-behaved linear set of equations. We can solve this, okay? Let me take a minute and talk about these loads for a minute. These loads can be anything. They could be point loads, they could be moments, they could be pressures, they could be unit displacements, they could be thermal loads, they could be inertias, they could be mode shapes. So if we laid strain gauges based on mode shapes, TrueLoad would directly calculate the modal participation factors based on the strain gauge measurements. So you get a direct calculation of modal participation factors for your mode shapes. So that's pretty incredible. But we can take that a step further. Let's say we had a plate that was bolted to a structure. So this is a square plate bolted down at 4 locations, the 4 corners. And we solved the plate for its mode shapes. So we got the modes for the structure. And then where it's bolted down at the 4 locations, we put XYZ unit displacements on our FEA model. And we laid strain gauges for all of that, the mode shapes plus the unit displacements. And if we went off and collected the strain data and went through the process with TrueLoad, TrueLoad would essentially be doing what's called a Craig-Bampton analysis. And a Craig-Bampton analysis calculates the flexible body response along with the ground interactions from the unit displacements at the boundary conditions. So we get a complete characterization of the dynamics just from a bunch of strain gauges. It's a pretty incredible technique that we've got here, that you can get that level of understanding about your parts with just some strain gauge measurements. Okay. So we've got this nice equation, strain times C is equal to F, and the only thing I haven't talked about here is C. So how do we find C? So if we look at this F matrix and we think of turning a load on as a 1 and turning a load off as a 0, then the F matrix becomes identity matrix. And then we can just do a pseudo inverse. So we've got strain times C is equal to I, pre-multiply by strain transpose, pre-multiply by strain transpose, strain inverse, and you've got C is equal to strain transpose, strain inverse, strain transpose. And that's what we pull out of the FEA model. So this is how we're pulling that correlation matrix out. And now the only thing we've got left to worry about now is the strain gauge placement. We've got millions of places to lay strain gauges. So how do we know where the right place to lay the strain gauges are? So if we look at our equation for the correlation matrix, you can see we've got this inverse in here. And inverses can be very poorly behaved. And that's not what we want. We want the best behaved inverse. So we recognize that the inverse of a matrix is defined by the cofactor of the matrix divided by the determinant of the matrix. So the thing in the bottom of the determinant, we don't want that to be 0. We want that to be maximum. So our objective function is to maximize the determinant of strain transpose strain. And we do this with this Galil-Kiefer d-optimal search algorithm, which is extremely efficient for finding the gauges. So this is how we do it. Okay? So this is how we find the strain gauges on the structure and get the optimal strain gauge placement. All right, I'm going to go through the workflow one more time, this time with a little bit of graphics behind it. This is our training example we use in our training. It's a very nice example. This is a headlamp on a motorcycle. And the analyst looks at this headlamp and says, geez, this headlamp's attached to the handlebars, and it's getting input from the handlebars, it's getting input from the front suspension, it's getting input from the frame and engine vibrations. So he says, this problem is basically a base excitation problem. So he's going to put boundary conditions where it's bolted in and put 10 G's X, 10 G's Y, and 10 G's Z. And he says he can combine any acceleration in the 3 directions to approximate a base excitation situation. So these are his unit loads on his FEA model. He goes in, solves the FEA model, and then launches pretest. And pretest loads up his 3 unit load cases automatically. And now that he's got his 3 load cases loaded up, now he's just got to select a subset of the model for possible gauge placement. So he's picking elements in the middle of the headlamp bucket and in the middle of the legs. And he's staying away from boundary conditions and staying away from RBEs in the model. He wants to be in nice nominal locations where he's going to have nice nominal strain response. So this is his choice for selecting the gauges, for the candidate elements for placing strain gauges. And then he tells TrueLoad he wants 6 strain gauges, and then TrueLoad will go off and draw up where the strain gauges need to go. And it shows him basically a position and a line that's showing the orientation of each gauge. And once he's happy with that gauge placement, then he goes off and places the gauges on the physical part and collects some measured strain data now. And the whole idea now is to take this measured strain data and turn that into loads. And he's going to do that with the TrueLoad post-test software. So post-test, we bring in the file from pre-test that's got that C matrix in it. We bring in the strain data from test, We basically push this magic button here to generate the loads. It's really that simple. But there are other things here that we can do. We can, map and drop channels. We can plot data. We can do lots of other things. But at the end of the day, it's really just bringing in the C matrix from pretest, strain data from test, and pushing the button. And when we push this button here, then what's going to happen is that TrueLoad is going to take the measured strain data, multiply it by the correlation matrix to generate the loading functions, and then it's going to take those loading functions and go back inside of the FEA model and pull out simulated strains at the gauges, and then it's going to generate for us HTML reports that with plots of measured strain versus simulated strain, so we can see how well those loads are duplicating what we measured. And once we're happy with all that, post-test will then automatically generate for us a QSE file, and the QSE file will have our unit loads from the FEA model mapped to the loading functions that were just calculated in post-test, and then we can probe any node or element we want for any data response that we want on the model. We can generate an operating deflection shape, and we can even go in and generate an FEA-based fatigue with one of our fatigue tools like FESave. So this is what post QSE is all about, is giving the tools to post-process the model. And this is fine. Now you can see what your model has done, what your part has done. But the whole point of this is that we want to do redesign. And in order to do redesign, then all we're going to do now is go back to the FEA model, and we can modify this model any way we want. So we could poke holes in it, we can thicken things up, we can change connections, we can do whatever changes we want. And then all I'm going to do is ask you to do is solve the model with the same 3 unit load cases, okay? So now the FEA solve is very simple. It's just a bunch of unit load cases. And then we take that FEA model and we go back to QSE, and we then just point the QSE file to the new FEA database, and then everything will be linearly superimposed properly, and you can see your response based on your design changes, okay? So it's a super quick way to get through lots of designs very quickly and easily, and understand your design changes. Okay. All right. I've got a workbench schematic here. I know many people are using ANSYS Workbench, so we're going to go through just how it looks like on the ANSYS Workbench. So for those of you using ANSYS, you know that basically you've got your structural component on the workbench, and then we can just come in and drag a pretest component onto that structural solution. This will launch TrueLoad, and we'll define our strain gauge placements. Once we're happy with our strain gauge placements, then we'll go into post-test, and we can connect post-test components to that pretest. And in this case, we had 3 physical tests we did. We brought that strain data into these 3 post-test components. This calculated the load. Now that we've got the loads calculated, then we can come in and then attach the QSE components to the post-test components. And then we can go in and query the model and generate operating deflection shapes to understand what we want about the model. And then let's say we wanted to do a fatigue analysis, we can bring those into our duty cycle manager. So I can say I want 5 repeats of the first, 10 repeats of the second, and maybe 30 repeats of the third. Mix those into our duty cycle manager, and then it will then just push that off to your fatigue software so you can do fatigue analysis. So even though this is Workbench, it's kind of a nice overall flow showing you how this all works in real life. Okay. So now we're going to get into a bunch of customer examples. This first one here is Honda. Honda had this oil passage on one of their engines, and they were experiencing some fatigue cracking. And so what they ended up doing is they ended up using TrueLoad to understand the internal pressures, the thermal gradients, and the mechanical movement of the ends of the tube here in order to understand the loads that were initiating their fatigue failures. And you can see here's a correlation plot of showing measured strain versus simulated strain that they were able to get on this component. And then once they had those loads, they iterated to come up with a new design that gave them the performance they needed. So they were able to solve this problem extremely easy. And if without TrueLoad, they would have had no tools to get after this problem. So it's just what TrueLoad can do. Here's a nice example from Aaron's. They're a lawn and garden manufacturer. They make these very high-end lawn and garden zero turning radius mowers. And so this, what you see here is an engine deck. This engine deck sits underneath the seat here, and the engine and transmission sit on this. And this structure was working just fine for Aaron's. They didn't have any issues with it, but their transmission supplier requested some additional airflow to the transmission here so they could cool the transmission properly. So they came and talked to us to see if we could help them out with it. And so working with the engineers there, we decided to treat this as a base excitation problem. So what we did is we modeled the engine and transmission as a lump mass, tied that into the structure here. And then since this is basically going over the proving grounds, which is a rough terrain, and it's going to get a bunch of inputs from the ground, we decided to model this as a base excitation problem. So we had modeled up 10 Gs, X, Y, and Z on the structure. So you can see these are the unit load responses here. Then TrueLoad said, place strain gauges at these locations here. So we've got 8 strain gauges laid on the structure. And we went off then and collected the strain data. So what you see here on the top left then is all 8 strain gauges being plotted up here in green. And again, TrueLoad takes the measured strain data, times a correlation matrix to generate the loads. And then once you get the loads, then TrueLoad goes back in and pulls out the simulated strain from the FEA model. So the green curves here are the measured strains, and then we've got the blue simulated strains plotted here too, and they're line on line. And down below here, we've got a cross plot of measured strain versus simulated strain. And you can see this is line on line, okay? We've got near perfect strain correlation here. And now that we've done that then, and we got these loads, we can generate the operating deflection shape. And now that we've got the operating deflection shape, we can go and do design iterations. Well, the interesting thing about this is that Aaron's has design guides for developing these engine decks, and they had one of their engineers work on their first iteration of this on their own. And they were so proud of the work they'd done. They had gone by the design guide, they'd done all the proper FEA modeling, and they had their first component on physical test, and they wanted to show us this part on test. And so when they took us down to the lab to show us this part on the shaker test, on the shaker table, the part had failed about an hour before we got there. And the part had failed in 1,200 hours. It's supposed to go 10,000 hours. And I said, perfect. Give me that FEA model. Let's take the loads that we've measured and run it through. So you can see we're getting very high stresses and strains on this initial design of theirs. And then working with the engineers there, we came up with a different design. Basically had 2 large holes, and the initial design was 2 layers of sheet metal riveted together. And this design was working great, but the manufacturing guys hated it. Okay, they didn't like having to have all those rivets and the 2 layers of sheet metal. So we had to go back down to 1 layer of sheet metal, and then we iterated over thicknesses. And by the end of the week, we had this solution. Okay, so next screen here, I'm going to show you the durability plots we came up with. Okay, so here's the fatigue material that they had here, and the yellow is showing 10,000 hours with their goal. And so what we want to see on these plots are yellow, green, and blue is what we want to see, anything exceeding 10,000. So their baseline was just fine. There's some red here on this just because of the RBEs on this model. And then here's the design that they failed in the lab, okay? So FE Safe was saying that this should fail in 1,000 hours, and in the lab, it failed in 1,200. So this is just perfect correlation as far as FE Safe goes. So it's just another confirmation saying we got the loads right. And then here's our first design. You can see we're getting very good fatigue results, and you can see the rivets on there. And then here's the subsequent designs on 1 layer sheet metal. And so by the end of the week, we had a design with the airflow they needed and with better durability than they started off with, okay? So this is what you can do when you understand the loading. You can actually get the designs right. And when we talked to these guys about it, they said, you know what, if they had to do this problem without TrueLoad, it costs them about $30,000 for every time they prototype parts and do the testing. It takes them about 6 weeks to do the design and procurement, and they're guessing at each step of the way for each design iteration. So if we did 5 design iterations, well, that's $150,000 in 30 weeks. And we did our whole project here in basically 8 days and under $1,000 worth of material, okay? So this is the order of magnitude savings that you can get when using TrueLoad to drive your designs, okay? When you understand your loads, you can actually make the right design decisions and get the right answers quickly. Okay, a couple more examples. This one here is a bulldozer from one of our customers, and basically when we talked to this company, they had already launched this bulldozer, and basically I had a meeting with the analysis manager and the test manager and their engineers, and basically they were telling us that in the development of this is that the FEA guys couldn't match anything in the lab guys couldn't match anything in the field, and each department thought the other department didn't know what they were doing. And they just looked at me, Tim, and they said, Tim, we don't care if your technology works. If it makes these guys talk to each other, we'll call it a win. So I worked with these guys, and we put up XYZ loads on the front of the blade. We put a load on this hydraulic cylinder here, and then on the back there was a mechanism we had to actuate. So we had 5-unit loads. We put 12 uniaxial strain gauges on here, so we had gauges on the arms and on the back of the dozer blade. And you can see on the top right, the green curves are the measured strains from this dozer, okay? And then the blue curves are the reconstructed strains from the loads that we measured. And you can see that these are correlating great. And these guys just thought this was fantastic. But they said, Tim, the real thing that we're really concerned about with is in development, they had issues with these forgings here and the welds around these forgings, and that was where their real concerns. So they laid some extra gauges of interest, like this gauge number 19 here. I got gauge number 19 plotted in green on this plot here. And then in TrueQSE, we probed the elements coming away from the weld in the FEA model and plotted up the strain responses there. And you can see how well we were matching at these hot spots. This is what happens, okay? When you get the overall flexibility and loading on the structure right, the hot spots come along for the ride, okay? This is what happens. And this is what our customers see all the time. Okay, last example, the Baja Car, the funnest one for the last, okay? So at Wolfstar Technologies, we hire graduate students from the University of Wisconsin to come work for us for summers. And a couple years back, I hired this graduate student, and he happened to be the captain of the SAE Baja Car team. And he says, hey, Tim, we want to use your software so we can do redesign on our suspension arms on our car. So what we did is we set up an FEA model with loads at the shock, loads at the wheel, top and bottom of the stabilizer links. So we had 11-unit load cases here. These are the animations of all of these unit loads on the structure. And then TrueLoad comes in and says, hey, place strain gauges at these locations. So basically you've got some on the arms. Most of the gauges ended up being on this forging here because all of the loads are on here, and you need to have gauges on the load paths. So it makes sense that they end up going there. And then they went off and instrumented everything up. Now, I have to emphasize that these are college students. So I had a graduate student and 2 undergrads working on this project. These guys only had FEA in school, so they had never built a real FEA model in their life. They had never touched a strain gauge. They didn't even know what a strain gauge really was. So they'd never touched a strain gauge. They'd never done any data acquisition. So they went from knowing absolutely nothing to doing this project. And I coached them along the way, but they did all the work. So they went from knowing absolutely nothing to completing this project in 6 weeks, okay? And they even did that, and they went through and they actually built jumps in the parking garage that we use for data collection. So we put the structure over these jumps, and they did some max brakes, some hard turns in the parking structure here. So this was our proving grounds. So these guys did a great job with us, and I have to emphasize, they did it all in 6 weeks in the summer on their own. So they did a great job with all this. And so here's our results. So we collected data going over that jump you just saw. And so here, so the green curves here, these are our 16 strain gauges that we had laid on that structure, the measured strain data. We took that measured strain data, multiply it by the C matrix. On the right here, you see the time histories of loading we calculated for our 11-unit load cases. And from those 11-unit load cases, then we can then go back in to the FEA model, pull out the simulated strains, and we got those simulated strains plotted up in blue. So green is measured, blue is simulated. Here's a cross plot of measured strain versus simulated strain, and you can see how well this correlation is, okay? And these are from from 3 college kids who have never done anything before, never touched a strain gauge, never really made an FEA model, and they're able to get this type of correlation. I would challenge any automotive company to show me a correlation plot this good, other than Honda, okay? And then once you've got the loads, you can generate the operating deflection shape. And now their point is that they wanted to do is they really wanted to go off and do a redesign on their arm. So they made up a duty cycle here. So they said they've got 30 hard brakes, 40 hard turns, 20 jumps in a proving ground. That's 5.6 hours of time. So when they ran their first design through FE-Safe was saying you've got 278,000 repeats until you start having failure, and that's just way too much. They were over designed here. So they went through an exercise of changing the FEA model, and they thinned up tubes. And what they ended up having to do is they could thin up all the tubes except for this diagonal tube here, and they end up getting a 25% weight savings. And so their life dropped from 278,000 repeats down to 12,000 repeats. Still plenty of life for a race car. And then they documented this all in an SAE paper that was published a couple years ago. And you can grab this off our website if you'd like. So, and this guy here is Paul Augustine. He's my grad student. He was a great guy. Okay, so that kind of wraps everything up. I see we've got some questions coming in. We've got some really great capabilities I didn't have a chance to even touch here today. We've got great tools for giving you tracking plots for your operating deflection shapes. We can do design of experiments. We can do gauges of interest very nicely and get you automatic correlation. We can take your time domain responses and push them into the frequency domains if you want. And we even have a 3D representation in STL format of your strain gauges, so you can import those into your CAD. So we've got some really great new capabilities. Love to take time to show you those and give you some more in-depth details about the product. But really, TrueLoad is the tool that can really help you get the strain correlation you need and give you the response, the loading that you need to do your redesign. And with that, I think we're done. Let's take some questions. This is the contact information for Wolfstar Technologies. I encourage you all to work directly with Vias since they're local to you, and Vias is our local expert. So definitely would very much enjoy getting a chance to work with you too on that. So let's get to the questions here. Let's see. So somebody's asking here, do we need to use rosette gauges? Okay, a lot of people like to use rosettes, and I understand that can give you some very good information about the strain state at a particular location. But TrueLoad by its nature is designed to work with uniaxial gauges. So by default, TrueLoad will put uniaxial gauges on the structure and distribute them across the geometry so you get the overall strain response in the structure. If you have existing data with rosettes, we can reverse engineer a rosette, but by default, TrueLoad won't work with doesn't lay rosettes. Okay. So somebody else is saying here, he's got a situation where he's got lots of contact nonlinearities in his structure. So if he's getting contact, how can he handle that? So contact is an extremely nonlinear situation, and the TrueLoad technology by mathematics is linear. But the way we handle contact, and this gets handled very efficiently, is if you've got well-defined contact on your structure, you can put unit loads at the contact location, and then TrueLoad will basically turn those unit loads on when the contact is happening. And if you don't have contact, then the loads from the contact area will be turned off. So we do an excellent job with handling contact. All right. So another person's talking about they've got structures and they like to put gauges on hot spots and do strain measurements in hot spots. TrueLoad by default does not work with hot spots. The problem with a hot spot is a hot spot's always hot. So if you're laying gauges in hot spots, we've got no capability to separate out the individual unit load cases. This is why we put strain gauges in nominal locations. We'll put gauges in nominal locations. Those nominal locations will have unique strain fields for each of your unit load cases. So we can then tell you which load cases are being turned on in any event. So if you've got hotspot gauges, we've got tools to allow you to lay those hotspot gauges, but we can't use those for load calculation. We can give you strain correlation plots of those hotspots, but we can't use them for gauge placement. I've got another one here. Let me see. For an offshore operator, what do they need to have a real-time load readout? Will they need an engineering workstation running FEA and TrueLoad, or they need a black box solution, no FEA analysts on board? So this is what we call our embedded technology solution. So we do have embedded technology solutions where you don't need to have FEA in the middle. We'll have FEA on the front end to help us place strain gauges on the structure, understand where the strain gauges need to go. But then once we laid the strain gauges, we can then take the correlation matrix that we extract from the FEA model, we can burn that onto a chip, and then we can basically set up real-time load monitoring and damage monitoring on your structure, and you can have a display with real-time readouts, and we can show, and we've got plots that can show you system degradation, and so we can give you some very important information that you can have during a real live health monitoring situation. So TrueLoad and the embedded technology solutions of TrueLoad can be used. We do need an FEA on the front end, but we don't need it on the back end. Okay, that was a great question.
Hi, Tim, I'm seeing another question here, which says, it was mentioned that you can look at existing workflows and provide feedback. Where can I send a workflow for your feedback? So yes, Shri did mention that in our intro. Shri, do you want to comment on that one?
Yeah, so the question is where to send the workflow, right? I mean, what's the process?
Mm-hmm.
Yeah, so definitely you can email us first, support@viascorp.com, and we can take it from there. Either through, I mean, we can even contact you directly your phone, and then we can have a mechanism of transfer of any files that we may need or discuss and that we may want to do. Yeah, please do write to us, support@viascorp.com, or even the phone numbers that we have listed earlier. Either way, you can reach out to us. Thank you.
Okay, I think that wraps us up for questions. All right. Is there anything else we need to say before we sign off here?
I think we should be good. We're not seeing any additional questions. Guys, this is our last call. If you have anything, please ask us. Okay, I think we can wrap up here. Thank you so much, Tim, for your time and for the amazing presentation.
Oh, looks like we have one last question here.
Yeah, so is it possible to have the presentation slide? Yes, this webinar has been recorded, and I will send out a recording to everybody who has attended today. So the answer is yes.
Great. All right, thank you, everyone. It was a real pleasure, and look forward to talking to you in the future.
Thank you, everyone.
Thank you. Have a good day. Bye.